And it has a bunch of registers that can contain SHA-1 hashes of whatever you want. If it sounds vague, let's get to it in a moment. So given this, what do you do with it? Well, so it has some nice properties. One of them being, actually, I think some of them can be, the really important ones can be distilled to this. That, let's say you create an RSA key pair. The private key will not leave the chip unwrapped. Again, it's kind of like a smart card. The public key is yours. So you can do RSA signatures using this, but you can't actually take the key out and put it somewhere else. Well, technically you can, but you have to create the key with those properties. But let's say we don't want that. So it gives you like a decent way to validate the identity of the machine. So think about, I want to use SSH to go from here to there, and I want to use public key with SSH. So normally what you do is you might use SSH keygen, you create a public key and a private key, you leave the private key here, you copy the public key to the server, and then you log in. But you can replicate these keys and you can put wherever you want, and even then, the protocol, when it does the key exchange, well, you know that, yeah, probably the right keys were used, barring any bugs in the system, but you don't know if this machine was used. So if for some reason you want to make sure that this machine was used, this can help. The stereotypical use case which the TCG wants to, the body behind this wants to advertise is that you put this chip in a system, you make the BIOS or the firmware aware of this, and when you boot the system, you put this tiny little piece of code which even runs before the BIOS. And you kind of implicitly trust this code because the manufacturer put in there, and it's supposed to be secure and all, and you trust the manufacturer. So this code will checksum the BIOS, for example, and it can put the checksum in one of these registers. So this thing has 24 registers. So it'll just do a SHA-1 hash of the thing and put it in a register. And another property of this hashing is that you can actually set these registers to a given value. You only provide them with a hash. And what the TPM will do internally is that it'll concatenate this new hash you gave them with the existing value, and then it'll do a SHA-1 of that, and it'll keep that in there. So you indirectly set it. You don't set it to a given value, and you can't like roll back to another value. So this way, the BIOS could checksum the option ROMs, it could checksum CPU microcode updates, it could checksum the bootloader. The bootloader could then checksum, the second stage bootloader, so on and so forth. You could checksum the kernel, and then you end up in what they think is a secure, authenticated boot. Well, you checksum the binary that you loaded, that's one thing, but I mean, once you checksum and once it's running, so it looks like they kind of try to hand wave some of these issues, and there's plenty of material on this, so I will only deal with what actually matters in this talk. So I showed those keys in the picture because we were talking about Mac OS X and the TPM. So yeah, so this is in the Intel Macs, and they're using encrypted binaries, and they don't allow you to run OS X on non-Apple hardware easily. So where does the TPM fit in that picture? The answer is nowhere. And yeah, so this is really a phantom menace. I mean, so much of build up for nothing. Unfortunately, that's the truth. Okay, so it's another interesting question. Did they think about this, though? I mean, were they thinking of using the TPM for, well, I don't know if they were or they were not, but have you ever looked at what it would take to create a system that does what they would have wanted? I mean, it can be summed up to this thing that you may have the TPM, but your system is not, I mean, there's no mandatory access control. There's no Palladium. So what are you going to do? I mean, yes, you can check some things as they load into memory, but then when you have supervisor access, you can bypass whatever you want still. So there's an important subtlety here that in the absence of mandatory access control, whatever you do here is just fluff, because eventually it all boils down to that normally how you would crack something else, like a software DRM. You would be able to do it here too. Would it be harder? Well, yes, in some cases. But, and it's not even a new concept. There was this thing called the Anderson Report in 1972, which I believe was the first thing to talk about the concept of a reference monitor. And they were talking about these problems even then, that how do you trust your systems? What is a trusted system? How do I know that it's not being compromised? And it turned out that, and people even then realized that, well, as long as you have this architecture where you have all these user programs and you have this really nice user kernel boundary which doesn't let you do any nonsense, and there's all the memories protected between processes and other processes and the kernel. But once you're in the kernel, you can do anything you want. And yes, you can have lots of mechanisms that that may tell you, I mean, that may be used to make it really hard for you to do that. But if you are the kernel, you can even rewrite some of those mechanisms. So it just becomes more difficult. It doesn't become impossible. Let's context switch once again. So Mac OS X has this hardware. I mean, Apple computers have this hardware. And it's not used. So we want to use it. How do we use it? Well, it's really well supported on Linux, actually. And it's the same chip. So there's a Linux driver for this TPM. It's the Infineon TPM. And IBM has been working a lot in this area. They even wrote this huge, like 100,000 line software stack for this thing, which is open source and available on Linux. And you can do a bunch of secure storage, all kinds of, you can do like a PKCS store that uses the TPM. You can use it with OpenSSL. You can do a whole lot of things. Many of them are interesting. But let's say we want to use them on OS X. So A, we don't want to rewrite that whole stuff. And B, ideally, we don't even want to rewrite the driver because it's not really new stuff. It's just, we just want the functionality. At least that's my thinking. So the Frankenstein nature of Mac OS X comes to our aid here. So when I say Frankenstein, it is Unix, it is Mach, it has BSD-style devices, it has dev nodes, it has an almost POSIX-compliant suite of libraries. But is this stuff really that, I mean, is it really that nice that you can just port whatever you want to it? So here's what I did. I don't want to program more than necessary. So I looked at the Linux driver, and it looks like a very well-written and small piece of code that essentially drives. So when you talk to the TPM, I mean, you access this thing on the LPC bus kind of like you access ISA devices, the legacy-style stuff. And there's a couple of registers, and you just do port memory mapped I/O to these things, and then you drive this whole thing. So I reckon that if I can write a driver for OS X that essentially re-implements in-bees and out-bees, so I don't even want to rewrite the Linux code. I just want to take it and drop it in and have it run. But it wants in-bees and out-bees. So if I can provide with Linux semantic style in-bees and out-bees, and I can give it a dev TPM-like device, then driver will work, it will have the same user space interface, and hopefully this giant suite of Linux software will also work. So one of the key differences between OS X and other types of Unixes is its driver library. And this is something that they inherited from NextStep. And the idea was that with their visual tools like the precursor to Cocoa and whatever, they made it quite easy to write most types of applications. And at some point, some people decided that, well, but writing device drivers, why is it black magic? Because, well, for one thing, you're in the kernel, you can't make mistakes, or you shouldn't make mistakes. But still, there are so many things to be aware of, like synchronous stuff happening, callouts happening, timers, blah, blah, blah. It's like, it's a madhouse. So how do you do something that's decently documented, and you don't have to worry about thinking about the nuances of the system. You can just care about your driver logic. So well, what they did was that they said, let's just make a driver toolkit that shields the user from the rest of the kernel. And like they have all these Objective-C interfaces, we will just give C++, embedded C++ interfaces in the kernel. And so much so that it actually works quite well. It really, really works quite well, whether you're writing a driver or you're hacking something. I'll give you an example. Let's say that you got this lump of Apple firmware from somewhere. You know, like it's an open firmware image that you want to update your machine with, or it's an EFI image that you want to update your machine with. So there's a kernel driver for this thing, and it actually represents the non-volatile memory of the firmware as a file system, or as a partition table. Now, what I could do is that I could write a driver that could inherit from one of these classes. And, well, there's a function that says, you know, read from this partition. There's a function that says write to this partition. And I don't even have to actually worry about anything. I can just instantiate it, you know, instantiate myself, and I get the benefit of everything that's on top of me. So you can do things like these. So it was quite trivial to write this driver. And did it work? I mean, what happened when I lumped this whole piece of Linux toolkit on top? Well, not initially. That's because Mac OS X is POSIX compliant, but almost. They do some weird things, and I mean, some of it is intentional, some of it is not. For example, they support, let's talk about like System 5 IPC or System 5 shared memory or semaphores or something like that. Well, they do support it because you can see the functions in the C library. Well, sometimes they forget a function. So like the function to delete it is there, the function to wait on it is there, but there's no function to create it, for example. So they do things like that somehow. In one case, I found that one of the functions was a stub. So I'm expecting to actually like block on it, it just falls through. And have you tried debugging stuff like that? Because like there must be a problem with what I'm doing. But so they do stuff like that. Because once you get over that stuff, which is not more than 10, 20 lines of code in this 100,000 lines I'm talking about, the whole thing does work. And yeah, so this is kind of a nice example of taking both a kernel driver from Linux and a software stack from Linux and just recompiling it with the right glue added, and it does seem to work. And well, that makes for some interesting experimentation. And I'll show you a few experiments. So no GUIs for me. I have the TPM driver loaded in Linux style. Let's go look at it. I'm expecting a question here. No question, huh? There's no Mac OS X users here? Okay, we'll come to that later. Okay, so this is a proc file system representation of the TPM, very Linux-like, very Solaris-like. No, not Solaris-like. Solaris uses it for actual processes. So there's two directories, key slots and PCRs. So I showed this briefly on my earlier slide. This thing, so when you create key pairs, I mean, this thing has a limited number of slots. You have to actually load this wrapped blob into the TPM to be able to use it. And it has 10 slots. And you can see there are 10 slots if you actually go in there. No permissions means no keys are loaded in that slot. And it has 24 of these platform configuration registers, the things that you use for storing those SHA-1 hashes.